Hi, guys. I think everybody. All right. So let me just put out a little notice about what you guys can expect this week. Just to kind of keep it in mind what to expect. So this week, we're going to finish today. We're going to finish chapter 1.5. Okay. We're going to do chapter 1.6. These are what we're going to do today, essentially. These you can expect homework and a quiz on Thursday. Okay. On Wednesday, we're going to do chapter 2.1 and maybe 2.2, depending on how far we get along on it, depending on how things go. It's not clear to me whether I'm going to put 2.1 on the quiz this week or have 2.1 homework due. I think, more likely than not, that'll be due next week. But I'll put a question mark on it because I think probably we'll have 1.5, 1.6. There's a lot of pretty important stuff we're going to cover in 1.5, 1.6 that we have plenty of things to put on our quiz. I'm going to think about in chapter 2, we might just keep for next week. But keep it in mind, we're going to do 2.1 and then 2.2 as well. Okay, so when you see, make sure you've got your homework set up for 1.5 and 1.6, that those things are going to be ready to get passed in. I graded and posted your quizzes last night. And so if you guys have any questions, make sure you also take a look at sometimes I'll write little notes, on the side. So like not only on the quiz itself, like I'll, put how many points I take off or maybe notes that I've written on there, but also along the side, like if I need to write something more extensive, I'll put it like in the little box on the side. I don't know how you see that, but some of you have some notes on there you may want to take a look at. I'll have the homework graded, later today, so you guys can take a look at that as well. Anyway, coming up. All right, so we'll make sure you guys have, if you want, your lecture examples for chapter 1.6 ready, because we'll probably start covering that today. And then on Wednesday, we'll do chapter 2. Okay. All right, so let's do a quick review, just a really quick refresh about where we were. So last week, we did chapter 1.5. We're going to finish that up this morning. We're talking about the mean value theorem. Now, the mean value theorem was an idea that basically said I've got this interval of x values from a to b. I've got my function. I can make a secant line between a and b. Okay, my function values are different from f of a and f of b, and a is less than b. When I get the slope of that secant line, remember secant line is where the line passes through our function twice. Okay. Now I can get the slope of that secant line, and if all those conditions are true, where a is less than b, my function of a, function of b are different values, that means that there's some tangent line at a value c happens between a and b. Tangent line is going to have the same slope as the secant line. How we found that point c was we solve for the slope of the secant line, set it equal to the tangent line, and then solve for c. Found that point where they're equal. Okay, so keep that in mind. Mean value theorem is an important idea because it's our secant line, our tangent line are parallel. Okay, they have the same slope. Rollies theorem was the same idea. It was just a specific case where f of a equals f of b. So the slope of our secant line is equal to 0. That means that our slope of our tangent line is equal to 0. Tangent line has a slope equal to 0 at one of our critical points, right? It's a max or a min point. Okay, so Rollies theorem is a specific case of our mean value theorem. Okay, for those of you coming in late, things to think about. We're going to finish 1.5. We're going to do 1.6. These are going to be today. Okay, these things you can expect to see on the quiz on Thursday, and then the homework for these will be due on Thursday as well. We're going to do chapter 2 this week, 2.1, 2.2 on Wednesday, and then higher two chapters, maybe on Thursday. I think probably we'll have those homeworks and the quiz on this material next week. Okay, but I'm just putting a question mark we'll see how things go. You guys want to come prepared to class on Wednesday with questions, or you can come to office hours for the homework if you want to ask. All right, so let's continue on with chapter 1.5. Chapter 1.5 continued. Okay, so chapter 1.5 has some good stuff in it. So what we want to talk about, some just some vocabulary first, because we're going to use this vocabulary when we talk about our first derivative test. So first, let's talk about the behavior of our function. Now, all of these things that we're doing, the first derivative, second derivative, ultimately we're going to do that in chapter 1.6, are to help us describe the behavior of our function. F of x is the thing that's doing something. And F of x is important because it describes climate change or, transmission of disease, in a population. We want to be able to model these things. And so I need derivatives to tell me the rate at which things are happening, or where critical points are, what we're going to learn, inflection points where things are happening. Okay, so all of this is to describe our function F of x. Okay, but let's talk about the first thing we want to think about is what's called increasing behavior. So if we have our function is increasing on an interval of x values from a to b. So this isn't a coordinate. This says our x goes from a until x goes to b, and this means it's an open interval where x doesn't take on those values. Okay, so if we say our function is increasing along this interval, let me write it in math and then we'll talk it out. So we say if f of x1 is less than f of x2 for all x is an element, this is an element of a to b. What that means is x element a to b, that means that x values, right, this is like x of I values, all these x values within our interval. Being an element of means I'm a member of this interval, a member of this group. Okay, so all x of I, so this is x1, x2, and then and x1 is less than x2. So all this means in terms of our graph, right, our x is increasing. I've got this a to b interval, our x is increasing. My function on this interval is increasing. This is my function here, right? So f of x1, x2, these values here, my function values, f of x1 is less than f of x2. Okay, all that means my function is increasing along this interval. I'm not even looking at what my function is doing outside of that interval, just on this interval. How I define this interval, we're going to talk about, right? I can define this interval based on a whole bunch of stuff. And we're going to talk about some of those intervals today. Okay, but it could be minus infinity to positive infinity. It could be 0 to 1. It could be minus 5 to positive 5. All these things are going to depend on criteria that we're coming up with. Okay, so increasing. Likewise, decreasing on our interval from a to b. So if it's decreasing, let's write it out in math and we'll draw a picture and talk about it. We say the function is decreasing if f of x1 is greater than f of x2 for all x1, x2 is an element of our interval a to b, and x1 is less than x2. Okay, so graphically, right, if it's decreasing, here's my x, here's my y, here's my a, here's my b, it's decreasing along this interval. Here's my f of x, here's my x1, here's my x2. Okay, so my function at x1 is greater than my function value at x2. Okay, along this interval from a to b, my function is decreasing in values. Okay, it seems, intuitively obvious, right? But we need to have this vocabulary so I can use it to describe my function, and we all know what we're talking about. Okay, increasing, decreasing, the third term is what we call monotonic. Mono meaning one, tonic meaning like behavior, right? So one behavior. So we say our function is monotonic. It could be monotonic increasing, monotonic decreasing, monotonic on our interval a to b if it is either increasing or decreasing on that interval. So it's doing one thing or the other, right? If along some interval it's only increasing, I say this function is monotonic increasing along the interval a to b, right? Or if it's only decreasing within this interval, I say our function is monotonic decreasing along the interval a to b. It gives me like a vocabulary that I can use to describe a function. And if you know the vocabulary, you'll understand it when other people use it too to describe something. Okay. So let's talk about how we're going to use our derivative to help us with this stuff. Theorem. This is a theorem. We're going to use the sign of our derivative to help us. Okay, so we're going to use this, and this is going to lead us into what we call a first derivative test. But for right now, let's just talk about the sign of the derivative. So we're going to say, let our function be differentiable. I'm running out of space. Differentiable on an open interval. It's important because if we're going to talk about its derivative, we want to make sure that we can actually take the derivative on this interval. Okay, so the first thing I'm going to say is if my first derivative of my function is greater than 0, which means it's positive, right? My first derivative tells me the slope of my tangent line. That tells me the rate of change of my function. If the first derivative is positive, right, for all x along this interval, then we say that f of x is increasing on our interval. Okay, we're only making a commitment to this interval. We're going to talk about how we define the interval in just a minute, so bear with me. Okay, so if f of x is positive, okay, then my function is increasing. We've seen this like with our parabolas, right? So I've got my parabola here. So if I'm looking at my derivative is positive, right, has a positive slope, my function is increasing right along this bound. And we're going to have to specify some interval over which that's increased. It's obviously not increasing everywhere. Okay, so now let's do the other part. So if our derivative, first derivative, is less than 0, that makes it negative for all x element of our, for all the x values within our interval, okay, then we say our function is decreasing on this interval a to b, which we'll have to specify. We're going to talk about how we're going to specify that. So here's our function. We've got some interval. Now in this case, right, my first derivative is negative, okay, along this interval here. Okay, this is important. This is leading us into our first derivative test, which we'll define in just a minute. We're going to go through a couple examples where I introduce this concept here, okay, and then we're going to talk about the first derivative test, and we'll go into great detail about how we're going to do it. Okay, so in terms of the sign of the derivative, right, I've got my lecture examples for chapter 1.5, and I'm going to do example number 8. So I want to show that my function ln of x is increasing. So my ln of x function goes like this. Okay. Now you may think, well, why can't I just graph these functions and look to see? Okay, you can, right? We're not judging you on the graph, okay? But you need these algebraic tools to help you analyze the functions, because ultimately, as engineers and scientists, we're going to be making functions that are so complex that to graph it, we're going to need these tools like this first derivative, second derivative, to tell us, right, what's actually happening in great detail. Like, where is it increasing? Where is it decreasing? Where is it concave up? Where is it concave down? Okay, so we're using more simple functions to illustrate ideas, okay, but you're going to be able to apply these fundamental ideas to really complex functions. Okay, all right, so now the first thing I need to do is I have to take the first derivative. Now remember, we're following kind of things in the book. We don't actually get to the power rule until chapter 2.1, I think is the power rule. So pretend, right, that we're doing our limit process and we're taking all these derivatives here. Okay, so my first derivative for my natural log function is 1 over x. This, right, 1 over x function is positive on the domain for all values. It's on the domain of my function, which is all values of x greater than 0. Okay, so my natural log function is not defined for values of x that are less than or equal to 0. So using that same domain, when I take a look at my derivative function, this is positive for all values, okay, when x is greater than. You can see that, right? So if I plug in x equals 1, x equals 2, I'm just going to get positive values on my first derivative. Okay, so then therefore, I can say that my function, not my derivative, but my function is increasing, okay, on our domain x greater than 0. Okay, so I'm not actually talking about the intervals. I'm going to define the intervals in a little bit. Okay, how do I get those? Okay, this is just to kind of introduce this concept. For the homework quiz, can we use the definition of the derivative process to find the derivative? Great question. So yeah, so when you guys when you do the homework for chapter 1.5 and 1.6, you can use the power rule. Okay. When you take the quiz for 1.5, 1.6, you can use the power rule for taking the derivative. Be very careful on the quiz that I just graded. I had to be really draconian on some of the points that I was taking off because it specifically said use the definition of the derivative. And so if you did the power rule, you lost almost all the points. And you want to lose the points on the quiz and not on the midterm and not on the final exam, okay? Because the quiz, I can drop a quiz grade, but I can't drop the exam or the final, okay? You will have a question on the midterm and on the final that says use the definition of the derivative, and you must do the limit as h goes to 0 of our average rate of change. Okay, that's our definition of the derivative. Okay, if we don't specify on the midterm and on the final exam, you can use whatever method you want. But if we specify that, you must do the limit process. So the quiz that we just took was all the limit process. You needed to show the limit for all those derivatives. For the quizzes, for the quiz going forward, you guys can use the power rule on it. Okay, because I know we're going to be getting into these things. It's funny, our book, I wish we had introduced the power rule earlier. It would have been a little easier before we got into all this stuff here. Whatever. All right. So example number 9. Okay, we're looking at this function here, x squared minus 2x minus 3. I'm just going to plot this out because I like to take a look at it. It's my parabola. It kind of goes like this. Okay. And then, you know, here, this is my lowest point right there. All right, so now what I need to do is show that it's monotonic. Okay, so I have to take the first derivative. All right, so I'm going to go 2x minus 2. I'm going to factor that out. Okay, so I'm going to get 2x minus 1, right? And I set it equal to 0. So x is equal to positive 1. It's where something's happening, right? It's our critical point here. Okay, so x equals 1, that's where something's happening. So I need to be able to take a look at my intervals. We're going to go into great detail about all of this stuff in just a moment. Okay, so if it seems like I'm hand waving it, I am on these first 2 examples because it's just to get you thinking about our sign. So our interval, I'm looking at all values up until that, and then my other interval is going to be 1 to positive infinity. So all values of x from 1 onwards. Okay, so on this first interval, minus infinity to positive 1, right? My my function is decreasing. My derivative is negative. So my function is decreasing. When I go from 1 to positive infinity, my derivative is positive, which means my function is increasing along this interval. Okay, like I said, these first 2 examples are just to kind of introduce this idea. We're going to go into great detail on how we actually work this through in just a minute. Kind of get you to think about my functions decreasing, right? My derivative is negative, my derivative is positive. It tells me something about my function. Okay. Right. So let's introduce what we call our first derivative test. This is important because on the exams, you'll be asked, you'll have a question that says, use the first derivative test to do something, right? And you must do the first derivative test. You don't have a choice. You'll have another question that says, use the second derivative test. You're going to learn that today to do something, okay? And then other questions where it just says, find stuff, right? And you can use whatever test you want, but we're going to have specific questions where we say, use this test or use that test. Okay, so this is our first derivative test. And we're going to do it for critical points or on critical points. Okay, so our first derivative test is going to go like this. So first off, I have to assume that my function is differentiable. I can't take the derivative. I have to do something else different. Differentiable. And we're going to let C be a critical point. For our critical points, right? So the critical points come from, I have a function, I take the first derivative, set that first derivative equal to 0, solve for x. Those are my critical points, okay? So I'm telling you C is going to be a critical point, okay? So then, right, the first thing that happens is, this is kind of like the theorem that I just put up. So f prime of x, my derivative changes sign from positive to negative at C, at that critical point. If that's the case, if my, right, so it's going to go, here's my function of x. My first derivative is positive. Here's C. And then my second derivative, my first derivative after C is negative, okay? If my first derivative changes sign from positive to negative at C, right, then we say my function at C is a local max. Okay, my function at C, if my derivative, my first derivative at C will be 0, right? That's my slope of my tangent line is 0, right? That's how I got the critical point. But this f of C value f of C, right, is my local maximum. Okay, C comma f of C is my point of local maximum. Okay, let's do the other one. My first derivative changes sign from negative to positive. What does that look like if my first derivative changes sign from negative to positive? Here's my function. Okay, my first derivative, remember I'm taking my first derivative, it goes like this. It should be attached to it. That's negative. My first derivative is now positive, right? And I've got this critical point that I solve for, right? This is C. Okay, and my function value f of C, okay? So if my first derivative changes sign from negative to positive, okay, at C, then we say f of C is, can you see it? A local minimum. Okay, we're going to go through a whole test case where we see what this thing looks like. Okay, but our first derivative test is using the sign of our first derivative around our critical point to tell us, you know, is this a local max or a local min? Okay. All right, so I've got example 10. We're going to actually use the first derivative test for this. Okay, so you can assume stuff in chapter 1.5 is using the first derivative test. Okay, so analyze the critical points of x cubed minus 27x minus 20. I'm just going to graph it because I like graphs. Let's do picture stuff. And we're not judged, we're not graded on our graphs right now. Like that, definitely. Okay. So the first thing I need to do is I have to take my first derivative of this function here. So 3x squared minus 27. Okay. Then I need to factor that and solve for x. So I'm going to factor, so 3 squared minus 9, 3x plus 3, x minus 3. I'm going to set that equal to 0 and solve for x. So x equals positive and negative 3. These are what I think are my critical points, possible critical points, right? Minus 3, positive 3. Okay. All All right, my next step is I have to figure out what are my intervals. Intervals of x values, okay? So this is the first set. Here's the second. I'm just going to put a little, I'll put an orange circle right here. Orange circle here and orange circle there. Okay, so my first interval that I need to think about is coming in from here. Okay, so my first interval, sorry, is going to look like all my x values from -infinity to -3. All the values coming in from way out until I hit -3. My next interval is going to go from here to here. Okay, that's going to be -3 to +3. And then my last interval is going to go from +3 out to +infinity. Okay, these are interval values of x. Okay. Right. Now I have to check my first derivative around these values. Critical points, which means I have to choose values of x from within each interval. Okay, and then test it on my first derivative. Okay, so I'm going to say my first derivative, I'm going to check my first interval at -4. Okay, so this is my interval. This is going from -infinity to -3. Okay, now I could have chosen any value I wanted between -infinity and -3. I could have chosen -100 million. Okay, don't kill yourself. Choose something straightforward. I chose something right near my critical point just because it was easier on the math. I plug it into my, I'm sorry, this is the first, I'm plugging it into my first derivative. Okay, my first derivative, when I plug -4 into my first derivative, right into this value here, I get +21, which is greater than 0, which is positive. Okay, take my first derivative, and I'm choosing a value along the interval -3 to +3. So 0. 0 is a really nice number. It's easy, right? So I plug that in and I get -27. Okay, plugging this into my first derivative right here. Okay, this is negative. Something's changing. All right, my first derivative, I'm going to choose a value within my third interval. So from 3 to +infinity. I could have chosen any value. I could have chosen 10. I could have chosen 100 million. Whatever you want, it's up to you. You're taking that number and you're plugging it into here. Okay, so don't kill yourself when you're like, don't pick a value that's going to be really complex, right? Make it simple. Get +21, that's greater than 0, that's positive. Okay, so I have my, around my critical points, I have a first derivative sign change, right? Positive, negative, positive. Okay, so I'm going to use the first derivative test. Okay, to actually analyze this stuff and come up with conclusions. I know some of you guys may have, like, you've drawn number lines and you've done, you know, with the arrows and the positive, negatives and all that kind of stuff. It needs to be very clearly marked, okay? Because often when I see those number lines, it's not clear if I'm looking at f of x, f prime of x, f double prime of x. It's better if you actually write a table out, okay? That line, I think, was like for the AP classes, they really liked to teach it with the line. But when we go to grade these things, sometimes when people look at the line, they don't grade it. You don't get as many partial credit points. So be very careful when you're doing the line. I'll take it, but it has to be super clearly marked about what it is that I'm looking at. And you need to tell me what values you've chosen within there to actually get to prove this point. This is all your work, like when you show your work on stuff. So the first derivative test. So I'm going to say c equals -3. I'm making conclusions about my critical points. So my first derivative changes sign from positive to negative, which means my function at -3 is a local maximum. Okay. So this function evaluated at -3 gives me a local max. My first derivative goes positive, negative. That means I'm at the top. Take a look at +3, my critical points. My first derivative changes sign. It changes sign on either side, changes sign from negative to positive. So therefore, f of +3 is a local minimum. Okay. This is our first derivative test to come up with conclusions about our function. Okay. You guys finish writing that, and then we'll do another example. I'll post these lecture examples to our modules page later today. They'll probably get put onto the modules for last week because that's where I first posted the lecture examples for this chapter. All right. Example 11, we're going to do a critical point without a sign change. So this is kind of a nice segue into our next chapter. So I'm going to just graph this out. So when I graph this out, it's a cubic. It kind of goes like, oops, I'm not going to graph it very well. Goes something like that. I didn't do a very good graph on here. This is our function value. Okay. Now I'm going to do the same steps. So I'm going to take the first derivative. I'm going to get x squared minus 2x plus 1. Okay. I'm going to set that equal to 0, factor and solve. So when I factor that, I get x minus 1 quantity squared. X is equal to positive 1 is a possible critical point. Okay, I have to check. I have to do my first derivative test to check to see if it really is a critical point. Critical point, right, means that I've got like a maximum or a minimum. Okay, so I'm going to take a look at what's happening. So my intervals are going to be minus infinity to 1, 1 to positive infinity. I need to check values of my function. So let's say here's my 1 right here. So I'm going to check values of my first derivative by choosing values within here. So I'm going to summarize it quickly. So what happens is when I'm doing this stuff, my first derivative, which is x minus 1 squared, right, is greater than or equal to 0 in both intervals. It's positive, right? So it's positive, positive, okay, regardless of what values I choose. You can kind of see that, right? No matter what I'm doing here, I'm squaring it. So this thing is going to be positive. If I choose values of x that are less than 1, if I choose 0, minus 1 squared is positive. If I choose values that are greater, I'm going to get 2 minus 1, positive 1 squared is positive, right? So my first derivative is always positive, okay, in both of my intervals. So then basically that means that my derivative does not change sign at our critical point, what we thought as our critical point. So therefore, c equals 1 is not a critical point. That means my function value here is neither a max or a min. Okay, it is important. We're going to see it's an inflection point. It's where the behavior of the function is changing, but in a different way than what our first derivative is going to tell us. So it's neither a max nor a min, which you can kind of see from the graph, but it's not changing sign, so it's not a max or a min. That means I need to do something else, which leads me very nicely into chapter 1.6. Okay, so this is the end of chapter 1.5. Okay, I'll scan in these lecture examples later today and then post them to our homepage modules. Okay, right underneath where I had posted the original copy of the blank copy of chapter 1.5 lecture examples. All right, so let's take a look. So chapter 1.6. Okay, so chapter 1.6 is called higher order derivatives. Okay, so higher order derivatives. So first off, we're going to talk about just our second derivative. Go through the same process of how I found the first derivative. I do the same process, and I use that to find the second derivative. I call this f double prime. I can call it y double prime. I can call it 2y dx squared 2f dx squared. It's not really squared. It's kind of how we pronounce it, but really it's the second derivative of y with respect to x. Okay, but I've got the second derivative happening here. The third derivative looks similar. I've got 3 tick marks there, right? For anything greater than 3, right? So if I do the fourth derivative or fifth derivative, I just ultimately write it as n. So f to the 4 of x means I'm taking the fourth derivative of my function with respect to x, y to the n. Okay, that would be an nth order derivative. So we call n is our order of the derivative. Now, some functions, right, like a polynomial, there's a limit to how many derivatives I can take before I hit 0, right? X cubed, right? There's only so many derivatives I can take before I'm basically just at 0, right? No matter how many other derivatives I want to take, I'm just at 0. But there are other functions, a whole class of functions where I can take an infinite number of derivatives. Okay, where it's the whole basis of topics for calculus 2 is how do we describe those types of functions? We take, infinite number of derivatives. But we call this n is the order of our derivative. And we consider n greater than or equal to 2 as a higher order. Okay. Just in terms of vocabulary. All right, so let's talk about what we can do with our second derivative. Already have all that. All right, so let's think about the shape of our graph. Okay, so this is the graph of our function, graph of f of x. Okay, because this is all ultimately to help us describe our function, right? Our function's complex, it's doing stuff, right? It's describing complex processes, okay? And we want to have all these tools that'll help us analyze that. So if I've got a function that's concave up, right? It looks like this, concave up, my function goes like that. Or maybe I just have a piece of it, or I have a piece of it like this. These are examples of concave up. I can hold it shaped up like this in the palm of my hand. Okay, the slopes of my tangent lines look like this. So here's my function. Let's just draw it. My tangent lines look like this. So it's negative, and it's 0, then it's positive. Okay, our slopes of our tangent lines on a concave up. If we've got a concave down, right, it's going to look like this. Okay, looks like, or I can draw it like just a piece of it. Pieces also make up part of our concave down. The slopes of the tangent lines look like this. Here's our function. And our slopes of our tangent lines look, they go positive. They go 0. And then they go negative. Right, so if I write this in words, the slopes of my tangent lines first are decreasing. They're 0, and then they're increasing. These are our tangent lines, right? Our function is decreasing. The slope of the tangent line is equal to 0, and our function is increasing because our slope of our tangent line is positive, which means that they're all showing positive slope. Here it's increasing to 0 to decreasing. Okay. Increasing, 0, decreasing. Okay. All right, so let's do a test for concavity. This is also a theorem. Just a test for concavity. Okay, so first off, we need to assume that our second derivative exists. You don't need to do this. Assume our second derivative exists for all x within an interval a to b that we're looking at. X is an element of a to b. All right, so first I'll say if my second derivative is positive. Right, so I've got my function, I take the first derivative, then I take the second derivative. Okay, for x values within some interval, that second derivative is positive. Okay, we're going to talk about how we define these intervals in a little bit. Okay, so if our second derivative is positive for all values of x within this interval, then we say our function, not the second derivative, but our function itself is concave up. Okay, so we're using our derivatives to tell us stuff about the function, remember. Okay, concave up. If our second derivative is less than 0, which makes it negative, for all x within some interval, a to b, okay, then we say our function is concave down. Okay. Second derivative is positive, concave up. Second derivative is negative, concave down. However you want to remember that. I always think positive is up, negative is down, whatever. That's just kind of how I remember. Okay. So now if we think about this on our graph, like how do we define these intervals, right? We said for these intervals a to b. How do I think about these intervals, right? So the points on the graph, where the concavity changes are called inflection points. This is P, C, that's like our critical point. F of C is an inflection point. Okay. How we figure out what our inflection point is similar to how we figure out our critical points, right? For critical points, we take our first derivative, set it equal to 0, solve for x. That tells us potentially where we have a max and a min. For our inflection points, right, so I have a max and a min like this, right? So my inflection point, right, is going to be this point right here where my concavity changes from, positive to negative, okay? Now, what I do for that is I take my second derivative, set it equal to 0, and solve for x, and I'm going to find that point where my concavity is going to change, potentially. Okay, so this, right, tells us our inflection point. So it's like I've got concave up, and I've got concave down, and I put them together into one function, and it looks like, over exaggerate that point. This point right here is our point of inflection. Okay, where the concavity changes. Okay, it's where our second derivative changes sign. Okay. So like our first derivative changing sign told us about max or min, our second derivative changing sign tells us about change in concavity. Okay, so it's another point of information. And this is important because right here, we're talking about a rate of change. My rate of change, right here, it's like how fast. This is still an increasing rate of change. These are still positive slopes, but this is a very rapid, a very steep slope. Now my slopes are slowing. They're not quite as steep anymore. Okay, so it's a very important thing because my rate of change is slow here. Past the point of inflection, my rate of change becomes very fast. Okay, so depending on where you are, the point of inflection is very important, just as our critical points are important. Okay, they tell us stuff about that function. Right. So we've got a test for inflection points. Also a theorem. So our test for inflection points is like this. So again, we have to assume that our second derivative exists. Okay, so if our second derivative exists, and if f double prime of c equals 0, I can solve for my second derivative equals 0, find that c value that makes that happen, and f double prime of x, my second derivative changes sign at x equals c, then we say our function has an inflection point at x equals c. Looking for my lecture examples. Okay. All right, so we're going to go through some examples. Just for today, I'm going to come back to example 1. It's not the best example. I'll do that on Wednesday. I want to do some other examples first that actually go into the great detail about the process on this. We're going to start with our example 2. Okay. So this says find the points of inflection and intervals of concavity of this function right here. 3x to the 5th minus 5x to the 4th plus 1. I'm just gonna, like I say, I like to graph things out just to see. We're not graded on this, so I can just kind of use it to help me picture what I'm trying to do. Okay, so there's my function, f of x. Okay, helps me visualize. All right, so the first thing I need to do is I have to take my first derivative. So my first derivative, 15x to the 4th minus 20x. My second derivative, f double prime of x, right? Same process. So this is 60 cubed minus 60x squared. Okay. Now I need to factor this and set it equal to 0. And then solve for those x values that are going to give me my second derivative equal to 0. Okay, so I'm going to do that. So when I factor this out, I'm going to get 60x squared times x minus 1 equals to 0. Okay, my values of x are going to be x equals 0 and x equals 1. These are my possible inflection points. I don't know that they're inflection points until I check possible inflection points. Okay, so x equals 0 and then x equals 1. Okay. All right, so let's take a look. So now I've got 3 intervals. So my intervals are going to be coming in from minus infinity to 0. And I'm looking at these values here. Now I have to go between 0 and 1. So I'm looking at x equals 0, x equals 1, right? And then I'm looking at from 1 to positive infinity. My intervals are here, right? And then here to here, and then here. So this is minus infinity to 0. This is 0 to 1. This is 1 to positive infinity. These are x intervals. Okay, I'm going to be checking values of x within here. Okay, now I need to do check the sign of my second derivative. Okay, so I'm going to set up a table. This is my work. Okay, how I used to show this. So I'm going to say what my interval is. This is my first interval. I'm going to choose values between 0 and negative infinity. I can choose -1, -100, -10 billion. Don't go crazy on it. Choose something that's straightforward. Okay, my test value is going to look like this. So my second second derivative evaluated at a value -1, which is within that interval. So I plug this into. I take -1. I plug it into here. Okay, and I'm going to get -120. So now, what do I see? My sign of my second derivative is negative. Okay, so what does that mean? My behavior of my function, what does that mean? If I have a negative second derivative, it means I've got concave down. Okay. Check our other interval. So my other interval is from 0 to 1. I have to choose a value of x within that interval. Plug that into my second derivative. I chose 1/2. It's straightforward. I plug it in, I get -15/2, which is negative, which means I'm still dealing with concave. Okay. got a third interval to deal with, so 1 to positive infinity. Or now remember, you can choose any value you want. Just do it correctly, and then, you know, don't go hog wild, just something straightforward. So from 1 to infinity, I chose 2. I plugged that into my second derivative, and I got 240, which is positive, which makes this concave up. So let's take a look at our table and then draw some conclusions about what we're seeing. Okay, so the conclusions we want to draw. So I'm looking at my second derivative, right? And I see I've got this, what I think is an inflection point at x equals 0, but right around x equals 0, my second derivative does not change sign. It's negative, right? Always on both sides of x equals 0. It's concave down, concave down. All right. So that means when I say at C, at x equals 0, C equals x equals 0, I've got no point of inflection. And the reason why is because my second derivative, x, does not change sign. I'm sorry, you can't see that. Does not change sign at x equals 0. Right? I'm looking at my second derivative, x equals 0. It's not changing sign on either side of it. It's still negative on both sides. Okay, let's check the other one that we thought was a potential potential inflection point. So on either side, right, from 0 to 1 and 1 to infinity, on either side of that, my second derivative changes sign from negative to positive, which means I go from concave down to concave up, right? I'm going from concave down to concave up. That means because my second derivative is changing sign, I have an inflection point. So this is a point of inflection because my second derivative changes sign at x equals 1. Okay. So this is your work, right? And we're using our table to help us make that decision, make these conclusions about what's happening with our function. So we find x equals 0, we'll find we would be doing a first derivative test on here too. So we would find that this is actually a local maximum, right? This is also a local minimum, right? And this is our inflection point. So most likely what's going to happen is x equals 0 is going to show up as a critical point, okay, when we do our first derivative test, and we'll see that's going to give us a local max, and then we're going to get a local min right here, okay? We do our second derivative test, it's going to show us, we have a point of inflection here, but not here. But we have to check, right? We have to check to be sure. So we make up a whole table. We've got these intervals, we're checking our values, we're checking the sign of our second derivative. Based on that table, I can come up with conclusions about what's happening. Okay. All right, so let's do another example. Example 3 says I've got points of inflection for this function here, x equals 5. I'm going to draw this out, x to y, and I'm going to draw this probably not so great. It's going to look something like this, and that actually goes to the origin here. Okay, so here's my function, something like that. All right, I'll tell you just kind of write just a little thing, does not exist at inflection point. Okay, I'm just giving you a clue ahead of time that this doesn't, we'll see why, okay, but I'm telling you ahead of time. So let's take our first derivative. So my first derivative is going to be 5/3 x to the 2/3. Okay, now I take my second derivative and I get 10/9 x to the minus 1/3, which when I write it out as a fraction looks like 10 all over 9 x to the 1/3. Okay, now I need to set this equal to 0 and solve for x. I'm in a problem here because I go to solve for it and I get 10 equals 0. So I have a problem, right? So x can't be equal to 0 because I'll get a divide by 0 error. Let's pretend, I'm going to pretend I live in a world where I can plug in x equals 0 that's how I'm going to get my second derivative equaling 0. Okay, so x not equal to 0, that means my second derivative at 0 doesn't exist. So let's write that down. So second derivative at 0 does not exist. Okay, so what do I need to do? So I need to think about what's happening on either side of that. So I'm going to go my second derivative is 10 over 9 x to the 1/3. This is greater than 0 when x is positive, right? I can, my second derivative, I can plug it in, I can plug in values that are greater than 0 into my second derivative here. And I'm going to get a positive number. It's going to be negative when x is less than 0. Okay. So that means that 0, 0 is a point of inflection, okay, of my function. Okay, so even though I can't get an actual value out of here, right, because it doesn't, my second derivative at 0 doesn't exist, okay, I still need to check values on either side of that point, okay, to see what's actually happening. And in point of fact, my second derivative does change sign, right, from positive to negative, which means I'm dealing with a point of inflection. Okay, so here, point of inflection. Okay, so just, you know, don't be stumped when you're working along and, oh, I can't solve for it. You know, okay, so f double prime doesn't exist. F double prime at 0 doesn't exist, but let me check values on either side of that. Okay, because something important is happening there. My second derivative doesn't exist at that spot, but what does it look like? What's actually happening? Okay. Great. I think what I'd like to do at this point is let me give you the second derivative test, tell it to you, and then we'll stop, and then we'll come back on Wednesday, and so you guys will have enough information to be able to do your homework or start your homework for chapter 1.6. Okay, so this is our theorem, second derivative test. And then at the beginning of class on Wednesday, we'll finish up the examples for chapter 1.6, and then we'll move on to chapter 2. So second derivative test is important. You're going to have questions on the midterm and final where they say, use the second derivative test to do something. Okay, so make sure we know it. So we're going to do something. So we're going to let C be a critical point of our function. And we're going to assume if our second derivative of x at C, of f at C exists, then we can make some assumptions, that we can do some tests. So we're going to say second derivative of f evaluated at C, if that is greater than 0, if it's positive, okay, then we can say f of C is a local minimum. Okay, my second derivative is positive. That means I'm dealing with concave up. That means my function evaluated at that C value is going to be a local minimum because we're dealing with the concave up. Okay, if my second derivative evaluated at C is negative, then f of C is a local maximum. Okay, remember our second derivative tells us about concavity, right? So it's concave down if it's negative. At C, my second derivative evaluated at that critical point, if it's negative, that means I'm dealing with a local maximum. And I have to do it. If it's equal to 0, it's inconclusive. You have to use it. It could be max, could be min. You need to use your first derivative test to figure it out. Use first derivative test. Figure out if it's a max or a min. Okay, that's the example that we don't have time for today that I'll start class off with next time, is that we'll have some where it's positive, negative, and where it's actually equal to 0, and then we have to go back and use the first derivative test on this one, even though I was able to use the second derivative test on this critical point here. Okay. All right, so I'm going to end here. And then, like I said, we'll pick up next time. Okay. And then take a look on our modules page. I'll post lecture videos, a copy of today's lecture onto our modules page, plus onto the YouTube channel. Okay. And then I think your homework assignments should be up already for this week. You guys should be all set. And I'll post the solutions for chapter 1.5 lecture examples. That'll be I'll post it in last week's module. Okay. Hey guys, have a great day. See you Wednesday.
Thank you.
Bye.
Thank you.
Thank
Take it
you.
easy. Bye.
Thank you.
Take care.
Thank you.
Bye bye. Take care.